Hello, everyone, and welcome to today's webcast, brought to you by Power Engineering Magazine. I'm Russell Ray, Chief Editor of Power Engineering Magazine, and your host for this hour. Today's event, Total Condenser Performance Workshop Tube Cleaning, will be presented by our expert, George Saxon of Conco Systems. But before we move on to the presentation, I'd like to share a few housekeeping details with our audience. This webcast is both live and interactive, so you can ask questions at any time by clicking on the Ask a Question button in the presentation window. We'll begin the Q&A after all of our speakers have completed their presentation. But keep in mind, you can submit your question at any time during the webcast. If you are running pop-up blocking software, you will need to disable it to view this webcast. In addition, it is recommended that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the home page at www.power-eng.com. Now it's time to introduce our speaker for the next hour. George Saxon is the President of International Markets at Conco Systems. George, the floor is all yours.
Well, thank you very much, Russell. It's a pleasure to be online with you today, and I'm looking forward to the next 45 minutes to an hour to begin our journey on achieving improvements in condenser performance, in this case particularly through condenser cleaning. Inasmuch, I think we ought to identify an area where we're going to start from, and that is with the basic assumption that you have some fundamental understanding of heat transfer and cooling water characteristics. What do I mean by that? Simply that we'll be addressing things that impact thermal conductivity, cooling water flow, and heat transfer. So with a basic understanding that fouled tubes can impede the condenser performance, we'll proceed with this session on cleaning. So what we believe and what I believe and why I'd like to take you on this journey is because achieving the perfect balance of condenser performance is certainly attainable. I see that it's possible for you to achieve that through cleaning, perhaps leak detection, and non-destructive testing as well. But today we're focused on cleaning. Now, implementing the strategies that we're going to deploy today or introduce you today will help you to minimize condenser-related outages and also to improve performance, and they will, in fact, result in quantified returns on investment. And I'll show you some back-of-the-envelope methods that you can use to demonstrate the improvements and the potential return. Moving forward, this Venn diagram identifies the three sections that I mentioned earlier. And you can see the sweet spot. That's what we call total performance. Today, the focus on cleaning is an area that we know you can achieve good results in. Together, when combined with testing and leak detection, you can get absolutely the best results. But in each respective area, it's possible to gain a significant improvement. So, let's focus on cleaning and fouling of heat transfer surfaces. What happens? Well, there's a loss of performance and potential output. So if the tubes are fouled, the heat's not transferred efficiently. Subsequently, the back pressure may rise, and inasmuch the cooling process is slowed down. In addition, there are consequences associated with other equipment. Let's say under deposit corrosion, hits through your tube wall, penetrates into the condensate, and inasmuch carries those contaminants through the boiler and up into the turbine. Well, let me give you an example of common conference references. One fellow says, you know, we track our boiler tube failures, and don't you know it, they come almost to the day 6 months after a condenser tube failure. Well, look, if the contaminants penetrate the tube wall and get into the condensate, they will go to the boiler. Consequently, they may also go up to the turbine. So now you have a machine running in the basement that typically is well maintained. However, you have a penetration or a failure, and now the consequence is damage to the other equipment. So I want you to keep that in mind when we talk about return on investment and the economic impact of condenser cleaning. Now this particular image shows a variety of condenser tube deposits laid out for you to easily review. They come in all shapes and sizes. And if you've had the pleasure to be inside the condenser, you'll know that some are very wet, some are very sticky, slimy, and some are hard. Here you can see the dramatic differences between deposition or particulate deposits, as well as scale, some debris, and some corrosion product. So when you are assessing the condition of the condenser and the cleanability of the condenser, you want to keep in mind what type of deposits you might see there so that you can select the best and most effective cleaning technology. So how do these deposits get there? Well, it's simple enough that in this group today, there are representatives from freshwater plants, brackish water plants, and seawater plants. Right? So the mineral content in these waters varies, but this is what occurs onto the tube surface. So within that water, give consideration to, for example, particulate fouling. It's simply debris that settles out onto the tube surface. It might be natural sediment. But typically, it's a result of low flow conditions. So if you have design information that says that the cooling water flow through the condenser is supposed to be 7 gallons or 7 feet per second, then in fact, that's what you should be achieving. If you're running through at 4 foot per second, then it's conceivable that you're going to have some accelerated sediment deposits simply because these particulates are falling out of the cooling water. Then, of course, there's the potential for scaling deposits. And how does scale occur? Well, in essence, basically the elements are so saturated, or the cooling water is so saturated with the elements that once the temperature reaches a certain level, these things plate right out. Now, it's inevitable that you're going to see some type of scale deposits in your heat transfer equipment, largely because the water will contain certain minerals that particularly behave in that way. So you see this on the inside of your faucet at home. This is in the condenser. Even if you had ultra-pure water, I would argue with you that you could see some scale buildup on the ID of the piping or the tubing over time. And that, of course, impacts heat transfer. It also accelerates under deposit corrosion. And if this scale redirects the flow of the water, it could ultimately result in erosion corrosion around the deposit. So removal of these scale deposits is absolutely essential. And it does not only occur in the areas where the cooling water reaches extreme temperatures. It can occur with moderate temperatures when there's a high mineral content in the water. But we're going to address how to deal with those things here today. This is a tube sample with under-deposit corrosion showing. Here is a stainless tube with deposits forming on the tube surface, and then there's a pit right there in the center. Looks like it's about 6 o'clock. Well, look, key points here. This deposit does not form uniformly on the tube surface. There are always clean surfaces adjacent to surfaces with deposits. Additionally, the thickness of the deposit may vary. In this case, the hard deposit in the center of the tube is significant enough to redirect the water flow and cause some washout or erosion. And that pit right there that you see at the bottom is, of course, the pit that shuts the machine down. It goes all the way through the tube wall and allows cooling water contaminants to penetrate the condensate. That pitting occurs underneath the deposits, and that's a primary example of why it's important to keep the tubes clean. Now, in other conditions, microbiological fouling might be your experience. Basically, that's bacteria forming a biofilm. This forms typically when cooling water is at low velocities, and it will support fine deposition, particulate deposition. So when the biofilm lies down, basically it allows the particulates to stick to it. And then that particulate deposit buildup accumulates, kind of like a snowstorm effect. That's happening on your tube surfaces. So you want to, again, remove the biofilm, and you'll have less particulates sticking to the tube surface. But this biofilm, or this bacteria, may also be corrosive for the tube material. Many of you have performed non-destructive testing, or you have seen microbiological deposits that actually eat through the tube wall. They burrow into the tube, and they ultimately cause tube failure. Again, keep the tube surface clean. This is a nice picture of a bacteria on a tube surface consuming material. It's exfoliating, and it's also going in through the ID of the tube. So you can see some of it occurring on the top of the tube, and what's happening on the top of the tube is also happening in the wall of the tube. And this demonstrates the example that I mentioned. Manganese, a mineral that typically forms a scale or is crystalline in nature. First of all, manganese is abundant throughout the United States and around the world, but particularly in this time of year as well. The manganese is run off from the autumn leaves and into the freshwater rivers, carries into the cooling systems. That's beside the point. The manganese is on that tube wall because there was a substrate of bacteria or a biofilm to allow it to collect. So without the biofilm, you got no manganese scale deposit. This manganese should wash right through the condenser tubing, but the presence of the biofilm allows the mineral elements of manganese to stick to the tube wall. As it accumulates, it's then affected by temperature and scales up. The thermal conductivity of manganese is very low, and inasmuch it causes a great deal of frustration for condenser operators when it appears in their condenser tubes. Don't fret, it can be removed. Right. In addition to deposition, microbiological crystallization, mineral content, there's general debris that may be coming in through the circulating water tunnel. It could even be part of your cooling tower. But in many cases, it's seagrass, leaves, heavy mud, sticks, things that aren't typically caught by the screens, the traveling screens, or in many cases aren't even caught by the debris filters. But what happens is this debris generates a partial blockage. It reduces the flow. One of the assumptions of the webinar today is that there is an understanding that low flow will negatively impact the heat transfer. So it's conceivable that even with the precautionary measures in place, like traveling screens and debris filters, that there will be an accumulation of debris or macrofouling in the condenser. For seawater plants, most common macrofouling is shells and sea life. Again, they're easily removed if you know what you're dealing with. Here's a photograph that I like, and I hope you like it too. It's certainly appropriate for this time of year. That's a tube sheet completely covered with leaves. Those leaves came in through the cooling water tunnel, and they have blocked the tube sheet. That's generating a very low flow condition. One might argue, remove the leaves and you restore the flow. Well, I would agree with you partially. But that low flow is doing what? Yes, it's causing the sediment deposit and the particulate deposits in the water to just fall right out and attach to the condenser tube. So not only does the tube sheet need to be picked and cleaned, but the condenser tubes also need to be cleaned and cleaned effectively to restore the performance of the condenser. Now, I did have the privilege to review the answers to some of the questions that were provided for your registration. And I did see that there is a nice variety of tube materials represented in today's audience. There have been references to copper, stainless, titanium, and also some references from the industrial side to carbon steel. So let me tell you a little bit about these three materials. They're all excellent tubing selections, but they all behave slightly differently. For example, a copper alloy condenser tube will actually kill some microbiological growth. The presence of the copper kills the microorganisms. The biofilm is slowed down considerably. However, while it sacrifices itself to protect from the microbiological deposits, it presents and forms an oxide, and this oxide grows like hair, and inasmuch it has to be removed from time to time because when it gets to a thickness, when it impedes the heat transfer, it's no longer working effectively to protect from corrosion. On stainless tubes, the most important thing about the stainless tube is to keep it clean. It's an excellent performing material. However, it does collect slime and particulate deposits. And one of the funny things about this material is it's used predominantly in the Midwestern United States. And in the Midwestern United States, there is an abundance of calcium in the cooling water and other, let's call them hard water conditions that cause scale to plate out onto these tubes. Easily enough, it's removed, but nonetheless, there is a loss of performance up until that time. And then there is the titanium tubing, which we see quite more frequently over the last 15 or 20 years, that provides good heat transfer characteristics. It also is, it does not corrode, and it has a very smooth surface. Now, people argue that they have installed titanium tubes and they no longer need to clean. Well, that's simply not true. I will say that they will have a longer incubation period from the initial installation until their first cleaning, but after the initial cleaning, the fouling will occur at the same rate as it does on the stainless steel tubes. So please keep that in mind. All of these materials do foul. Carbon steel, not photoed here, will present a high amount of corrosion product, which is effectively removed in the cleaning process when selecting the appropriate cleaning technology. Now today we will specifically address mechanical cleaning, but I do have to mention some things about the prevention of fouling through appropriate water treatment. I'm sure that each of you have experience in making selections on water treatment conditioning. And perhaps scale inhibitors or dispersants are being used. You may have tried some very clever pH control techniques to reduce fouling in the condenser. If you have a significant amount of biofilm, it may be that you've purchased truckloads of biocides or dispersants to keep the mineral content and particulates in suspension. So these practices are underway. They get better and better. The most important thing is to have the right strategy for the right cooling water condition. The water treatment program typically will not eliminate the need to clean the condenser. And while the company might be spending a significant amount of money in the water treatment program, it should also be accepted that the tubes will foul and they will need to be cleaned. Now, under mechanical fouling conditions or mechanical fouling prevention, there are screens, filtration systems, even online cleaning systems that are used to maintain the cleanliness of the condenser. And of course, you can even ramp up your circ water pumps and increase the flow to get a better result. But that's going to cost electricity to run, house electricity to run the pumps at a higher rate. So I showed you the leaves that came in through the screens and through the filtration system to plug the tubes earlier in the presentation. Well, a continuous online cleaning system may have great difficulty operating under those conditions. Simply said, that if the leaf is blocking the tube and the water can't go through there at its full rate, neither will the continuous online ball cleaning system. So some of the economic consequences to condenser fouling are listed here. So you may also use these as indicators to investigate what's happening in the condenser. You have an increase in turbine back pressure or unit heat rate. The cooling water is being discharged at an inefficient consumption or rate or temperature. CO2 emissions can be reduced dramatically, and you can be an environmentally friendly operator if you're a coal plant. Let them know how well you're maintaining the condenser, and you can literally reduce the amount of CO2 emissions by thousands of tons. It's in the literature. You can find it, or we can provide it for you if you'd like. But the big one is reduced generation capacity. You may be the plant manager, or you may be reporting to the plant manager. If you walk into his plant and you can see that the megawatt outputs signals are not at the designed capacity, it may be, that it's an indication that things aren't going too well at the plant, and you're looking for those lost megawatts. Well, many times they can be recovered in the condenser. And also, I mentioned earlier about the tube failures leading to damage in other equipment. I used to think that was a stretch. Oh, come on. What about the vibration on the turbine, or what about those contaminants all over those turbine blades? Where does that come from? Oh, it comes from contaminants in the condensate. So you can throw the turbine out of balance. You can spend the weekend in the boiler cutting out tube samples to find out that it was foreign matter in the condensate that ultimately caused the damage. But be aware of that. And tie those to your ROI rationalizations. So if you're being challenged on your tube cleaning procedures and processes and decisions, don't forget to provide a satisfactory economic return statement. And include some of these things, because it's all true. Now, other diagnostic techniques include simple things like deposit sampling, heat transfer testing, use of a fouling monitor. You may have your own special program that you're running performance calcs on your PC, or you may go in there and take a look inside the tube via a borescope. and decide for yourself if the tube's clean or are they not. The ASME Performance Test Code 12.2, 2010, actually incorporates deposit sampling as an effective way to assess whether or not the condenser tubes are fouled. I.e., if there is a question as to whether or not the tubes are fouled, then 1, take a look with the borescope. 2, put a Pro Series TrueFit standard tube cleaner through the tube and collect the sample. If a deposit is present, clean the condenser tubes. So it's quite straightforward, and that performance test code is largely based on the idea that you're accepting a new condenser or evaluating the performance of an operating condenser. But we know that the presence of deposits will result in a compromised heat transfer. So you might have taken that tube sample. We're on this journey improving condenser performance, right? You know a little bit about deposits now, heat transfer characteristics, what's happening, and in as much, you went in there and you did a fouling test. You did some sampling. Well, you got this deposit. Now you go to the lab and say, what is this deposit? Here we show elemental analysis with 10 to 20% manganese and 5 to 10% iron. Well, that means I need to come up with a cleaning solution that's going to be able to deal with that type of deposit. We know manganese is crystalline. It's very thin, it's hard, and difficult to remove. Iron is more porous, but nonetheless, these are the two primary minerals that are present in the cooling water. There was no loss on ignition done on this sample, so we don't know how much of that total deposit was organic. But if we did do a loss on ignition test and we burned off all the organics, we would know how much microbiological matter we were dealing with. Here's the second part of the deposit sampling. It's called the deposit density test. Here are 11 samples ranging in deposit or weight in grams per square foot of 17.5 to 0.14, or total grams of 217 to 1.79. So 217 grams of deposits times 20,000 tubes, that's a lot of deposit carrying around in the condenser. So you want to clean that up. Oh, well, if it's 1.79, well, I'm not as concerned. But if you can see here, these different weights tell us that there is a random distribution of fouling throughout the condenser. This was actually 11 samples taken from various locations in the condenser. So now the challenge is to organize for cleaning with a technology that will remove deposits as light as 1.79 grams and as heavy as 217 grams in each and every tube. So, first slide I showed you earlier where deposits don't form evenly on the tube's surface. Second slide here I'm showing you now that deposits don't form evenly throughout the condenser. So those are variables that you have to be prepared for. What other variables? Well, the cooling water type and system. Fresh water, brackish water, seawater. Is it a once-through condenser? Is it a double-pass condenser? The temperatures are higher on the outlet. Is it a multiple-compartment condenser? What's the tube material? The deposit types? Are we addressing corrosion as well? How many tubes and what are their size? Do we want to do this job in a weekend, or do we want to do it over 6 weeks during the overhaul? Which cleaning system are we going to use to achieve the results? Right? So those are relatively few variables given the significant projects that you're working with in other parts of the plant. And they're manageable. And in essence, this is what I like about the cleaning aspect is that this is one area that you can get your head around, take an action, and get an immediate result, and then move on to the next problem. But you'll know that the condenser is clean, and as a result, you'll have improved output. Excuse me. Okay. So, you may have an effective water treatment program, but you may also want to clean your condenser by a chemical dissolution method. You may adequately be cleaning the condenser, in your opinion, at the current time with hydroblasting. You may have a job at a plant, or you may be engineering a plant that's been operating for some time with a continuous ball cleaning system. Or you may have been exposed and are using a mechanical removal technology. Again, the registration information indicates that there's a fair amount of you using one or two of these types of cleaning. So I think that the group is well represented, and I'll be fair and objective in my review of the matter. In essence, chemical dissolution can be extremely complicated, and depending on what types of chemicals you are using, there's the associated aspects of the disposal of the chemical. Now, if you have an organic treatment or an organic acid that you're going to use, and it's going to remove the scale deposits to a satisfactory level, you may be getting a good result. But I would argue that in addition to the chemical cleaning, you may wish to have a high volume of water for neutralizing the chemical and removing it from the ID of the tube, as well as putting a tube cleaner through there to remove the residual deposits. So two things are accomplished when you do that. One, you neutralize the chemical, so there's no threat of any acid attack going forward. And two, you remove all the residual deposit that the chemical was not able to remove, because it's generating gas and there will be pockets of materials left in the condenser tubes. For hydroblasting, many of you are familiar with this technology. Basically, it's the use of 20,000 psi or greater to remove deposits from the IDs of the condenser tubes. It has been rendered unsafe in most refining and petrochemical facilities, and in the power generation industry, typically it's associated with the randomness of the cleaning action. I may push my lance through the tube at 2 minutes a tube. Gary Fisher, our other presenter, may push that lance through at 30 seconds per tube. So his tube is not going to be as clean as the one that I am using, or the one that I am cleaning. Additionally, anybody who is performing the testing in the laboratory will run the lance over the tube until they get it to the level of satisfaction that you desire it, and then it won't be repeatable in the field. So those are some risks that are taken. Surface roughness remains. So in addition to deposits on the tube surface, you have some corrosion matter that's not effectively removed. The corrosion matter behaves in the same way as the residual deposits. Particulates accumulate on there faster, and it snowballs. Now, it can be dangerous as well for thinning tubes and tube sheet joints. It cannot be used in the presence of coatings. In fact, high-pressure water and ultra-high-pressure water is what is used to remove coatings for replacement. So that's risky. And there are a reasonable amount of injuries associated with using this technology. Now, I want to appeal to your environmental side and show you a very simple comparison of the amount of water that's consumed for high-pressure water washing. let's look to the right of this slide, scenario 3, over 5,000 tubes. The water usage to clean that many tubes with the mechanical cleaning system manufactured by Conco is 8,750 gallons. To clean the same tubes with high-pressure water, it takes over 2.3 million gallons of water. That's, what do we have there? A 26,400% increase in the amount of water consumed just for cleaning the condenser. So I would argue that the environmental impact of utilizing high-pressure water is not sound, and it can be improved. So reduce your water consumption and put that stuff on the shelf, and let's think about an alternative solution for that. Now, online cleaning systems are used to effectively maintain cleanliness in the condenser while the plant is operating. So it's important to know that the system isn't particularly designed to clean up the tubes. It's designed to maintain the cleanliness of the tubes. So during the overhaul, you want to clean the tubes, return the unit to service in as-new condition, let the continuous online ball cleaning system keep the tubes clean, and then again address the tube cleanliness at the next overhaul. Simply put, the system will not remove large amounts of deposits. In fact, balls may become hung up on deposits and obstructions. Well, look, the balls are designed to travel through the tubes at random, right? So there may be an uneven distribution of the balls. Deposits will accumulate. If you have obstructions, sticks, sea life, leaves, cooling tower fill inside the condenser, then it's unlikely that the balls will go through the tubes at all. If they do go through the tubes, they may become lodged. When they're lodged, no cooling water is going through the tube at all. No flow, no heat transfer, less heat transfer surface area, and then the condenser performance begins to erode. Now, too aggressive passing of the balls, high frequency in ball passage, may also result in tube wear. Nonetheless, there are a lot of parts associated with this particular equipment that must be maintained. A crew must be trained appropriately, and the expenses and ball consumption can cost more than 2 mechanical cleanings per year. So, while these operating costs are high, if the condenser is large enough, the maintenance of the cleanliness during the operation period will be improved. Now, we like the mechanical cleaning options. Why? Well, because they're the most frequently chosen, and they're generally applicable and effective, and of course they're fast and easy to use. They're very safe. More importantly, we can always see an improvement in heat transfer and provide protection from under-deposit corrosion. Flow is then restored, and the efficiency of the condenser is returned to its as-new state. Now, you might say, how quickly can that be done? Well, it minimizes unit downtime because 5,000 tubes can be cleaned during a 10-hour shift. Well, that's rather rapid. So, if you double the shift, you can actually clean 10,000 tubes in a day. That means that in periods of peak demand, you can actually climb in there, clean the condenser over the weekend, and bring it back to service early Monday morning, ready to make money. Also, There are a myriad of types of mechanical tube cleaners that are effective on all types of deposits. And they can remove, just like it says on the slide there, fouling deposits, corrosion products, physical obstructions, and address tube surface roughness. And if there is a desire to perform a cleaning assessment study, the tube samples can be sent out to providers so that the cleaning can be performed and the results can be assessed. This is the standard of the industry. The TrueFit tube cleaner, manufactured by Conco Systems. It's heat-treated, spring-loaded carbon steel. It's got some features there that are outstanding for effective tube cleaning. The variety of designs of tube cleaners are typically designed to address a type of fouling so that the architecture of the blades can remove the mineral content, the microbiological film, or the corrosion product that's present. They're spring-loaded, and the radial design blades match the idea of the tube. Now, your condenser tubes came with a specification. They are size, so they give you an OD diameter, and they give you a wall thickness and a tube length. And this is fairly straightforward. In fact, one of the event downloads is the Heat Exchanger Institute, HEI, data sheet. That data sheet is a blank form, but inasmuch you should have one of those for each one of your condensers or heat exchangers in the plant. That will provide you with the information that you need. So, when the TrueFit tube cleaners are manufactured, they're manufactured to a specific size. Other manufacturers might manufacture a tube cleaner that claims to be satisfactory for a range of sizes. Well, it's just not possible, because understanding the geometry, if the tube cleaner is adjusted to be too small for the radius, then the tube won't be effectively cleaned. If it's too large, it has the potential to damage the idea of the tube. So you have to be extremely careful in selection of mechanical tube cleaners to know that they're built to the specific size of the tubing at your facility. In this case, this manufacturer does that. Now, they go through the tubes, the scale, and the corrosion, and soft deposits are removed. At this point, I believe we have a video that we're going to show you. By now, then, you've seen the video of the C4S tube cleaner traveling through the tube. The tube cleaner was inserted into the tube, and it was propelled with 300 psi water pressure. The radial design blades put pressure on the ID of the tube to remove the corrosion product and the deposits, and all the deposits are removed out ahead of the tube cleaner. there are a number of types and styles of mechanical tube cleaners that are available. The first grouping is all-purpose tube cleaners. These are industry standard tube cleaners for both soft and hard deposits. There's another group of tube cleaners, specific application tube cleaners. These tube cleaners are designed for unique fouling scenarios and perform differently. In fact, there's one cleaner there, I think it's called the Type H, which is currently being used by some of our clients in the U.S. Navy, and over tens of thousands of these are used regularly. So they all are produced in large quantities and are readily available, regardless of the size of the tubes that you have and whether your cleaning exercise was planned or unplanned. And then there's U-tube cleaners used for feed water heaters. So that's the portfolio of mechanical tube cleaners that are available in the industry, and they're very useful and effective. Another interesting aspect of the mechanical tube cleaning is that the propulsion system or the pump system is small and easy to maneuver around the plant. So here you see a Pro Series tube cleaning pump, and we call it the Pro Series because it's what the pros use to clean the tubes. Service companies are utilizing that equipment as well as our own service division. And a water gun. So that's how the tube cleaners are propelled through the tubes. Here's a nice photograph of a technician inside the water box shooting condenser tubes mechanically. So he's running 300 psi water at 25 gallon per minute flow. He'll shoot all those tube cleaners through the tubes. They'll go to the outlet end, collect them, clean them up, and use them again. They're reusable, and each tube cleaner can be used from 8 to 12 passes depending on the type of deposits present. Now, one thing I mentioned in the beginning of our journey was that we were going to give you some information about tube cleaning. And so you have that information now. So I'd like to go into the next part of our journey, which is what are the costs, what are the return on investment? How does it look? How can I write this up to get it done? Let's take a typical 625 megawatt unit, right? 24 from the curves and the surface area and the heat transfer calculations, I can determine that approximately 24,000 1-inch 20 tubes would be required to meet that demand. Estimated cost to mechanically clean that would be $32,400. All right? I know from industry reports and information that the cost of fuel for a change in 0.3 of an inch in back pressure on a 600 megawatt unit would be $562,500. So with a simple rise in back pressure of 0.3 of an inch, it's costing my plant $562,500. For the mechanical cleaning, I put out 32.4, return 562.5. That's $500,000. So the net present value of that investment is $530,000, or a return of 1,636%. That can be measured immediately on return to service. That, in fact, is remarkable. And that's the type of return you should be getting on your projects. And when you're weighing your projects against other larger projects, make sure you present the potential return, because somebody always wants to spend more money on a bigger project with a smaller return. You're going in to ask for a little bit of money for a big return, so make sure you represent the return. Here's a classic case. This is a plant in the Midwest, a freshwater plant with deposits on the tube surface. Inasmuch the changes were 0.8 of an inch and 1.4 of an inch of mercury in sides A and sides B. I simply presented to you 2 slides ago that you could recover 0.3 of an inch. Well, you can recover a lot more than that if it's there to recover. That resulted in a net increase in output of 27 megawatts. 27 megawatts? That's more than a field of windmills. 27 megawatts, that's a whole other unit on your facility. That's a couple $100 million of investment to build a plant for 27 megawatts. And of course, you even saw an increase in circulating water flow. And made it all the way to 6.5 feet per second. So how do you make your quick calculations? It's not overly complicated. Make some assumptions. 0.3 of an inch of mercury can equate to 10% improvement in condenser performance. 10% improvement in performance can ultimately achieve a 1% improvement in heat rate because it's directly correlated. So an example for a 600 megawatt unit on 0.3 of an inch of mercury is a 10% cleanliness factor with a 1% improvement in heat rate, or 6 megawatts. What's that mean in replacement cost to the company? Well, that means that at 1 year times 70% capacity factor at $60 a megawatt times 6 megawatts, that's $2.2 million return or savings. So that's in fact remarkable. Additional benefits include the economic benefit, the reduced cost, the immediate return on investment, the recovery of increased lost megawatts or increased generation capacity, fuel savings, the reduction in CO2 emissions, and the extended useful life of the condenser. And I might add that you are able to download this presentation under the events materials if you'd like to get that. Now, here's a case. First case. 18,390 pounds of calcium carbonate scale removed from a condenser. That's the real result. This condenser had never been effectively cleaned. Years in advance, it had been cleaned with high-pressure water. It was mechanically cleaned. These were the deposits removed. Cleanliness factor in the condenser, that's a measurement calculated to assess the performance, went from 34% to 93% on one condenser and 37 to 90% on the second condenser the company cleaned. That's an outstanding result as well. Here's an example of tube testing done in the laboratory. As found tube condition at 83% cleanliness factor, and the clean tube at 91.5%. That's approximately a 10% improvement. And right next to it, you can see a 20% improvement from 73.6 to 94.1% improvement. So I run that back through the calculations, and I say these are good exercises for mechanical cleaning. In this case here, case 3 is a nuclear plant. You can see that the nuclear plant not only has fouling in the tubes, but it has cooling tower fill and continuous online ball cleaning system balls blocking and lodged in the water box and in the tube sheet. So the important thing is to go in there and clean each and every one of those tubes effectively and restore the condenser to its as-new condition. The results in this case were a recovery of 2.5 megawatts, basically 60 megawatts a day. Cleaning cost was recovered in 2 days. So, in summarizing this cleaning section, I can only say that it's possible to achieve an outstanding return on investment from tube cleaning. To be wary, but not only clean for performance reasons, but also economic reasons, and to prevent tube failures. Now, inasmuch when you are proceeding with the cleaning, know that the results should be achieved. If they are not, then you want to look into alternative methods for cleaning that will be able to handle your site-specific conditions. And in most cases, mechanical cleaning has a solution for you. With all that being said, I'm going to open up the floor for questions.
All right, very good. Thank you, George. That was a lot of great information. You covered a lot of ground in a very short amount of time. Thank you so much. As George said, it's time for the Q&A portion of today's webcast. Joining George today in the Q&A portion of the webcast will be Gary Fisher. Gary is a sales manager for national markets at Conco Systems. Thank you, Gary, for joining the discussion.
My pleasure.
If you have a question for George or Gary, please click on the Ask a Question button in the presentation window. You can type your questions there, and don't forget to hit send. Type it, send it, and we will have one of our speakers answer the question. And it looks like we have several questions already, so let's get started. We're going to start with question number 17 on your chart here. Here's the question: with the more rapid velocity in the tubes and the low velocity in the water box, do you consider that fouling starts on the tube sheet and progresses into the tubes? George, Gary, want to take that on?
Sure. This is Gary Fisher, and welcome to everybody who's joined. Really, the fouling begins when the heat process within that tube, when the steam begins to go over the tube. So the fouling begins inside the tube in most instances. You will get debris, you will get mud, you will get some sort of fouling on the tube sheet, but in most instances the fouling will begin within the tubes, and what you're going to get is just some loose debris, usually on the tube sheet, that you can usually take off with a power washer of some sort, and it will take that off. You do have instances, though, where a calcium or a manganese will leach out and begin to form on the tube sheet. But in most instances, it happens within the tubes themselves.
All right. Very good, very good. We'll move on to question number 20, and this question is regarding the TrueFit cleaner. This question is this: is there a maximum amount of pre-existing debris within the tube, in that there are real concerns over getting the cleaners stuck in the tubes?
Okay, this is Gary again. You can have that situation. We have trained crews that go out and they inspect the tubes whenever they go in to do the cleaning. Typically, if we are able to get in there before the cleaning, we will have one of our technical sales staff to go in and look at the fouling itself. Most instances, I will say, that using the proper cleaner, you can remove all that fouling. But in some instances, calcium, for one, calcium carbonate, if you allow the calcium carbonate to build up to such an extent that it is too thick, then we can't even get a cleaner down the tube. Then it's possible that you have too much fouling, and it would be difficult to clean that tube using mechanical cleaning. Our recommendation, though, is if you have that situation and you know you have calcium carbonate in your tubes, you're going to have it this time, you're probably going to have it next year and the year after. Stay on top of that process and clean on a regular basis, and you will be able to remove that. So it's possible, but in most instances, we're able to get in there and with the proper cleaner, remove everything that's in that tube.
All right, very good. Thank you, Gary. Let's move on to our next question. Our next question is this: it's question number 21. How do we understand the cleaner is not dimensionally worn and still keeping its accuracy? Gary, George?
This is Gary again. That's an excellent question. You have to make sure that the cleaners you buy are of high quality, first and foremost. The type of cleaners we use are a carbon steel, and they have some tension to them so that they can fit into the tubes tightly. You have to inspect those, and our supervisors do when on the job. But typically, you can shoot a specific type of cleaner X number of times. For example, a metal type cleaner for us, you can shoot 12 to 14 times down the condenser. After that, pretty much you know that the cleaner itself has been worn and it's no longer effective. If you're going to use an H brush, you only may get 6 to 8 passes on one of those cleaners. So this has been done, extensive research has been done on this. We've got a lot of experience. The heavier the fouling, the less times you can shoot that cleaner. However, we have, like I said, done a lot of experience, with a lot of experience and a lot of testing, have come pretty close to what's optimum for our type of cleaner. But you have to watch the type of cleaner that you do purchase on the market, because there are cleaners that will not put up with some heavy fouling nearly as well as others. So.
All right, very good. Thank you, Gary. Our next question, question number 15, actually comes from a college student. They are a student studying power engineering. They are in their second year, and their question is this: how does the condenser increase the efficiency of a turbine? Gary? George?
That's excellent. We actually have, under the event resources section there, if you go under the question box, there's 4 downloadable PDF files. One of those files is mechanical tube cleaning procedures. Another is the data sheet. Another is practical application innovation of tube cleaning technology. And then there's this PDF. But if you read the practical application of innovative cleaning technology, it goes into this situation right here. And really, there's 2 problems that you have when you have fouling. You have a loss of heat transfer, and you can have under-deposit corrosion. And that fouling is detrimental to the heat transfer, which causes the efficiency of the steam condensing unit to fail. And you get lower, resulting in a lower vacuum or a higher pressure, and thus a less efficient turbine operation. So the cleanliness of that condenser leads to how effective that turbine can operate. And in the long run, if the condenser is over-fouled, if it becomes fouled to an extent that it is not condensing the steam, you can actually lose megawatts at the turbine itself. But if you download that article, the practical application and innovation of cleaning technology, it goes into that very question quite well, and I would recommend it for you to read, and I think it would be helpful.
All right, very good. Thank you, Gary. We have time for one more question, and I'm going to point you to question number 19. During George's presentation, he mentioned ball cleaning, and the questioner is asking this: can you comment on the traversing brush cleaner systems?
Sure. That's a different type of system. That is actually what we call our Excalibur. It is a brush at the end of a shaft, and the shaft is connected to a motor, which actually rotates that brush. Typically, that type of cleaning system is used on specific applications, such as if you have U-tube heat exchangers or heat exchangers where you cannot take off the back end so that you can't collect the cleaners themselves. You would be able to use this rotating brush. The rotating brush is effective. It can operate quite well under the right characteristics and under the right situation. It is a little bit slower to use, but it is very effective under the right application. We very rarely, in fact, I can't remember a time when we used it within a condenser. It's typically used in heat exchangers. So that's the type of rotating brush system I believe that we're speaking of there.
All right, very good. Hey, thank you, Gary. Thank you, George, for your information. I think we'll conclude the webcast right there. As Gary mentioned, Conco has provided 4 PDFs on this topic. You can find that information on the viewing console under Event Resources. Once again, thank you. You've been tuned in to Total Condenser Performance Tube Cleaning, brought to you by Power Engineering Magazine. On behalf of Power Engineering, I would like to thank today's speakers for their time and willingness to share their expertise. This presentation will be archived within 24 hours and can be accessed from the home page at www.power-eng.com. A reminder email message for the archive will be sent to registrants, complete with a direct link to the archive. We thank you for joining us today, and we look forward to seeing you again at future webcasts. Take care, everyone. Take care. Bye.